Okay, so I want to back up to some Cal 3 stuff, talk about differentials. And you actually did differentials in Cal 1 the first time. That's when you did like substitution and integration. You know, if you had u as some function of x, then du was f prime of x dx. It's the very last thing you cover in Cal 1 and the very first thing you cover in Cal 2. But this talks more than just about integration. We do this in substitution to replace the dx part in an integral with a du part. But it also says that if you've got some variable u that depends on some variable x, then a small change in x can predict a small change in u. In fact, how much u changes when x changes is given by this formula right here, f prime of x dx. So if you know the formula upon which u depends on x, then, and you want to find out what will a small change in x do to that formula. And this is actually used in things like chemistry and physics, in measuring different quantities. If you know that the temperature of a certain object depends on some other factor, like its specific heat or something like that, and you get a formula for how that works, you want to know how much, if that changes, that deep independent variable changes, how much does the dependent variable change as a result? Well, you can use this right here. Okay, where we're going to end up using this is actually, and I'll just write this with our notation of y instead of u. We want to extend this to talk about when we have a function that depends on multiple variables. Okay. So how do we do that? Well, when you have a function that depends on multiple variables, does anybody remember what dz is equal to in that case? What's the differential of z when z is a function of x and y?
Partial of z and y.
Yeah, so it's like that tree diagram. However many variables you have, you'll have three terms. You know, if you have two variables, you have two terms, three variables, three terms. It's dz is equal to the partial of f with respect to x. We'll use this notation for right now. Times dx plus the partial of f with respect to y dy. Okay, so just remember some of the pieces here. These partials mean whatever the whatever the function f over here was, then taking the derivative of f with respect to x means treat y as a constant and then derive it with respect to x. And then partial with respect to y means treat x as a constant and derive with respect to y. Then the dx parts are just like we were talking about up here. This dx, right, represents a small change in x. So a small change in x, you multiply that times the derivative of the function. That'll tell you how much y will change as x changes. Now, if you're talking about a function that depends on two variables, then a small change in both variables can predict what the change in that dependent variable will be according to this formula, right? Okay, so now how do differentials relate to some of the pictures that I've got down here? How do we use them practically? So that's what I'm going to do next here on the screen, is I want to point out that if you've got some function f of xy, so we're thinking again z as a function of xy, that would be graphed as something like this paraboloid down here. If that happened to be the function that I was talking about right there, then when you graph these things in 3 dimensions, what you think of as z is the height of the function at any given coordinate point on the xy plane. So for every point down here, we go up to a certain height, we find a point on the plane, that height is z, and then this point down here has coordinates xy, 0, because it's on the xy plane. Okay? So given some function, one way to, I guess, visualize what's happening with that function without having to graph it in 3 dimensions is to examine what are called the level curves. Do you remember talking about level curves of a function? Right? It's basically your contour map, right? Or, if you go hiking and you've got a topographical map, a flat map, but it's got all the lines on it that tell you all the heights, or I guess all the points on that surface that are the same height. So when I graph something like f of xy equals k, that's a 2-dimensional graph, okay, of 1-dimensional curves, I guess one way to think of that. Which is where you get this picture right here, right? So curves are lines, but you can graph them all on one 2-dimensional plane. But you think of it as you have a series of different heights, k, here. And so for each one of those, you correspond with one of these lines, right? That's representative of that particular level curve. There's a nice little applet that you can go run at mathinsight.org level sets to see some of these things, but that's actually not vital to you being able to do the homework for this section. Okay, what I really care about is given any particular k, like if I've got f of xy equals k, is one of these curves. Let's say it's this curve right here. Okay? For a specific k. The question is, pick any point on there, what's the slope of the tangent line? What's dy dx at that point? And how do we get there from f of xy equals k? Well, actually, what I'm going to do is I'm going to do the differential on both sides of this. We can determine the slope of the tangent line by first taking the differential of both sides of that equation right there. Because if you do that, you'll get on the left-hand side something like this form. Partial f with respect to x dx plus partial of f with respect to y dy. And the right-hand side is just a constant, so you get 0. So you solve for dy dx, and that's where your slope comes from. Okay, it's basically implicit differentiation is what it is. But you can also think of it in terms of its differentials, because that becomes f sub x dx plus f sub y dy equals 0. Oh, I'm mixing my notation here. Sorry. I've been using the Leibniz, so I'm going to stick with the Leibniz. Partial cap f with respect to x, partial cap f with respect to y. Solve for dy dx. So you get this when you solve, right? And the types of problems we've been working in this chapter, when they're in normal form, are things like this, okay? So the question is, under what circumstances can I go from here to here to here, back to here, where that's now the solution of that right there?
If the function is separable?
Well, not exactly, because separable meant I can move the x's and the y's around. It has to do with how is this f here related to this capital F right there. Okay? There will be certain circumstances where I can find a cap f where this f here is a quotient of negative capital F sub x, or sorry, sub y, or partial of f with respect to y over the partial of capital F with respect to x. Okay? So when capital F is appropriately related to little f, we can find a solution. Actually, probably a better way to say that is, or when such a capital F exists. Dot, dot, dot. That is, we can find a solution. Okay, so it's kind of muddy right now. It'll become clearer as we start to do some of these problems. But again, what it boils down to is I'm going to start with an equation that looks like this. dy dx equals little f of xy, right? And that's saying I know the slope of the solution at any given point is the function f of xy. I also know that the slope of any given level curve of some function capital F looks like negative partial of f with respect to y over negative partial of f with respect to x. And so if I can find a capital F where this formula here is the same thing as my given differential equation, then I will have found the solution, and it will look like this equation right here. Okay? So here's how we do that. By the way, the equations for which we can do that are going to be called exact equations. So given an ODE that's written in this form, the easiest way to tackle this question of whether such an f exists is to convert it to differential form. Do you remember what differential form looked like? On like the very first day or second day of class, I told you all these forms. There was the general form of a differential equation. There was a normal form, which is what we've been working with mostly here, dy dx equals something. There was also a differential form.
Are you recording this?
Yes. Because I've already lost you and you have to watch this multiple times. So. dx plus n of x, y, dy equals 0. Now don't give up on me yet. If what I've said so far is confusing, it gets a little clearer as we get down further as to why the techniques. Yep. So there's a lot of preparatory material on this one, more so than the others. You recognize that form? I talked about m's and n's before, but we can convert a differential equation into this by killing a cat, right? Multiplying through by dx, and move all the, group all the dx parts together, all the dy parts together. That word should be form. I will point out that for a given differential equation, that form is not unique. What that means is you can apply some different algebra techniques and end up with forms that are the same differential equation but have different m's and n's involved. But one thing that is key here is that it's got to be 0 on the right-hand side. I'm going to pause for a second. Dang it.
I was going to ask, and I was like, no.
I paused it to do all this stuff on the board. All right, so I have no idea where I left off on the recording, so I'll post a filled-in part of these notes, but I think I left off talking about converting to exact, right?
This part made the most sense out of all of
Okay.
this.
Maybe I'll re-record it, I don't know. Again, convert something to this form. It's not unique. Now, we're solving this kind of differential equation by asking, does an f exist? So that if you take its partial with respect to x, you get m, and you take its partial with respect to y, you get n. If that's the case, then the solution is going to be that f, whatever it is, equal to constant c. Okay? So how do we check if that f exists? We check now by taking the m and the n and doing the partial with respect to the other variable that appears in the differential. So you've got m dx. M's the thing times the dx. Take m sub y. You've got n times dy. Take n sub x. If they're the same, then we'll move forward from there. If they're not, there's another technique I'll show you in a minute where we can try to manipulate it into one, but that doesn't always work.
Because our m and x are unique. Because they're non-unique, could it be possible that that we is it possible to mess up our conversion and have them not be equal?
Yes, it's possible, but not on the types of problems. I mean, it's going to be real simple to convert, and you just do the most obvious way to convert. But there are ways to mess it up, so it's not exact. But when you mess it up, usually that's the type of problems we'll be able to fix later on. So what I was alluding to earlier is what's way down here at the very bottom. I guess this is page 4. Return of the integrating factor. I'm going to multiply in something to make it exact. Okay? Under certain circumstances, I'll be able to do that. Okay. So once it's exact, the question becomes, how do we find the f? Let's just, before we even do that, how we find the cap f when we know it's exact, let's verify that one is exact, okay? I've given you one that's already in differential form. Let's check if it's exact. Okay, so what's your m?
2x,
And your n? So what's m sub y? Treat x as a constant. So 4xy. The x stays there because it's a constant, just like the 2 stayed there and you multiply it by 2. And then plus 0. And n sub x, treat y as a constant, so the y just hangs out. And you get 4xy, okay, equals, which means exact. All right. Now that 4xy is not useful in the actual solving, but it's the check that makes sure that it's exact, that says that the following technique will actually produce a solution.
Oh, this is all just the check.
This is to make sure that this is the right kind of equation for which this technique works. It proves that such an f exists. Now we got to find the f. Okay? Yep. I was like, again, let me just restate our goal. Goal, now find an f such that capital F sub x is m and capital F sub y is n. Then f equals a constant is the solution. It's not as complicated as you might think. I'm solving 2 different minor differential equations here of the best possible kind, meaning that all I have to do is integrate, right? What I'm trying to find is a function whose derivative with respect to x equals m. That's a question you asked in the middle of Cal 1. If I gave you a function, find the function whose derivative is that. That's integration. It's anti-deriving. It's indefinite integrals. Except now you've got extra y's thrown in that you ignore and treat as constants. Okay?
Which is easier?
What?
Which is easier?
What do you mean? Which one of these 2 equations?
No, it's easier to do partials than anything else.
Yep, because you just treat that thing as a constant. And you're now integrating, thinking only with respect to one variable, so the other one just hangs out as a constant. But the one trick that you've got to remember when you do that is that your constant of integration can also now depend on the variable that you're not integrating over. All right, so here's the method. Let's walk through this. First thing I'm going to do is I'm going to start with the m. And you can actually start with the n. Either one of these will work. But let's say we start with the m. So pluck the m off that equation and say, I want to find capital F so that the partial of f with respect to x is m. So what I do is I integrate m with respect to x. Treat y as a constant. That will find the function whose derivative with respect to x is m. But you'll have a constant when you do that. Your plus c, right? Whenever you do an indefinite integral, you got your plus c. But the plus c is a constant only with respect to x, which means it could change with y. So this constant now is some function of y. I mean, because think about it. If I said, let's say m is x squared, right? And I want to find any f whose derivative is that. So what I do is I say f is the integral of x squared dx, right? Which would be 1/3 x cubed plus a constant, right? But that constant could be anything that depends on y, because if that's my f, then what is f sub x? It's x squared, right?
Right, but anything limited to y.
I could put sine of y, I could put y squared, I could put plus y to the 1,000th power, right? All of that still makes the derivative of this with respect to x squared, right? So what I do is I put an arbitrary g of y there.
And then when you go to the end, you just match them up.
Exactly. Now I've got a potential f, and what I do is I take the partial of f with respect to y. That is, now take f sub y set equal to n. That's what I'm doing on step 2. And I'm going to solve for g prime of y. Because think about it, if you now take the derivative of, something like, say that's a y there, right? If you want to take the derivative of that with respect to y, you've got to take the derivative of this thing, right? But in general, you're going to take the derivative of whatever the arbitrary function is here, so you're going to get that f sub y would be x squared plus g prime of y, right? Because the derivative of this thing that has no x's in it with respect to y will be just an ordinary derivative. Okay. I'm spending too much time explaining everything when it'll make a whole lot more sense when we just do it. Now we know g of y has to be something, so we integrate g prime of y to get g of y, and then we plug that back in up here. So you'll know what this is. You'll plug in your g of y up there, and you'll say, I know what f of xy is, just set it equal to a constant, and that is your implicit solution to the differential equation. Step 1, integrate m with respect to x. Be sure to add your constant function with respect to y. Take the partial of what you get with respect to y and set it equal to n. Solve for the g prime. If you did it right and it's exact, when you solve for g prime, it won't have any x's in it. It can't, because it's an ordinary derivative with respect to y. Then you integrate that to figure out what g actually is and plug it back in, and then you have a solution. All right, so let's do that. First of all, check if exact. We'll call this step 0.
Yes, it's exact.
M sub x, nope, m sub y.
2x.
N sub x,
2x.
they're equal, right?
Yes.
A lot of times you can just eyeball the thing and know it's exact. It's not nearly as hard as I made it sound. All right, step 1. Okay, so f of xy will be the integral of 2xy minus secant squared of x dx plus some arbitrary function of y.
Just a quick question.
Yes.
The n to y equals 2x, we got that from...
I looked at this, right? This is m.
Yeah.
And then I take the derivative of that with respect to y,
Oh.
which is just 2x, and that's a 0. Because you treat x as a constant. And then I looked at this guy here, and I took the derivative of that with respect to x. See how I'm doing the opposite, right? The opposite one's there. And it goes back to the fact that it's the mixed partials that have to be equal to prove that there is an f. So I know m is f sub x, so I need f sub x y. So that's why I'm going to do the partial with respect to y. So I'm going to do my. And I'm going to do nx, and if those are equal, then I can proceed. All right, now let's integrate 2xy minus secant squared to x with respect to x. It's x squared y minus tangent of x plus some function of y. There's your f. Now, step 2. This function is the function whose partial with respect to x gives me m. Now let's prove, or let's find g so that f sub y is equal to my n. So what is f sub y?
X squared plus 2,
X squared plus 2y.
or 2y.
Your n is your f sub y.
Oh, sorry. Yes, you're telling me what my n is. I want to know what's the partial of this with respect to y.
Oh, right. It's x squared plus g of y.
G prime of y, right? Because you're taking the derivative with respect to y. Whatever g is,
So
to get the derivative, you're just going to do g prime of y.
x squared.
Because there's no x's in it, it's just the ordinary derivative of g.
Just gonna x squared minus y squared.
Okay, so again, what I'm doing right here is taking partial of f with respect to y. Okay, and now here what I'm going to do is I'm going to set that equal to n, x squared plus 2y. Set f sub y equal to n. I've taken this here, put it right there. And I've taken this here and put it right there. So if you did this right, the g prime of y should only be dependent on y. There should be no x's there. Right? Because see what happens? You with me?
Yes.
And now, what's g of y? This is step 3. Integrate is the integral of 2y dy, or y squared. So now you take this, you found your g, right? Integrate g prime to find g, and now I'm going to plug it back into capital F. So capital F of xy, so I'm not going to write the xy. Capital F now is x squared y minus tangent x plus y squared. And you might verify that f sub x equals m and f sub y equals n. You should be able to check that now. I have now found a function such that if I take its derivative with respect to x, I get the m. Right? What's the derivative of this with respect to x? 2xy minus secant squared of x. Check. Okay? What's the derivative of this with respect to y? 2xy plus, sorry, x squared plus 2y. X squared plus 2y. I have found an f that meets our criteria. Okay? So the solution, in step 4, the solution to the differential equation is f equals a constant. Namely, x squared y minus tangent x plus y squared equals a constant. This solves that differential equation. The curve that satisfies this equation, okay, has the right slopes at every point on its curve to match the original problem. That's the solution. Now it's implicit. In this case, it's actually kind of hard to solve for y, so we're going to leave it in implicit form. Sometimes it'll be easy to solve for y. If you can solve for y, solve for y. But why is this one a mess to solve for y? When you look at this, you see the y squared and the y. So getting it by itself, you'd have to use like the quadratic formula to do that, because it's quadratic in one. So we'll leave it like that. But that solution right there does satisfy the original differential equation. Okay, so there's quite a few steps you got to wrap your brain around. 1, you check if it's exact, or I should say 0, you check if it's exact. If it is, then you start dissecting the exact parts, right? The m, the n, to get to the f. You start with m, integrate with respect to x, then take the partial of that with respect to y, set equal to n, plug your, or I guess then you'll find your g prime of y, integrate that to find your g, plug that g back into the f, and you're done. All right. Do another one. All right. Step 0. Is it exact? So how do I check?
M sub y. Okay.
N sub y, which gives me
E to the x plus x e to the x.
right? Treating x's as constants, so e to the x is a constant. So a constant times y is just that constant when you take its derivative. And x e to the x is a constant.
So the derivative with respect to y.
Right, I'm doing the first equation, which is m, with respect to the other variable than the differential that appears next to it. And then n sub x, we would check. There's n. First times derivative of the second, plus second times derivative of the first. So first times derivative of e to the x is e to the x, so x e to the x, plus second times derivative of the first is just e to the x. Notice those are equal. So yes, it's exact.
So
Now I'm going to throw a curveball at you. It's easier to integrate n with respect to y than it is to integrate m with respect to x. You know, what I did before was I said I need to find m, the function that when I take its derivative with respect to x gives me this. Integrate that, get a plus g of y, take the derivative of that, set it equal to this. There's no reason why I can't do the exact opposite. Why not integrate this with respect to y, take the partial of that with respect to x, and set it equal to this? Works the same way. All you got to do now is choose, is this easier to integrate with respect to x? It's not when you recognize the substitution. This one's easy, this one
We just did.
Right, but look how easy this is with respect to y. The point is that I'm trying to make, and the reason why I'm doing this, maybe this isn't the best example of one that's really hard. There are some that are really hard. You need to be able to choose which way to go. The reason I like the second one with respect to y is that y's just show up. I mean, it's very easy, right? What is n of x, y? We would do the integral of x e to the x plus 2 dy. So, what is that with respect to y?
X, y, e to the x plus 2y.
Plus
0 g of x?
g of x, okay? I think the book tends to use an h for the x's and g's for the y's, but it doesn't really matter. Whatever you call it, it's some function, right, of the other variable. That's your f. So now, I would do, what is f sub x equal to? All right, so treating y here as, again, a constant, you got x times e to the x, so you get the first times the derivative of the second, which is x, y, e to the x, plus the second times the derivative of the first, which is x, y. Wait, yes? Yes.
Y e to the x.
Yes, thank you. Y e to the x plus 0 plus h prime of x. Okay, so I'm going to set that equal to n, no, m now, 1 plus e to the x times y plus x e to the x y. I'll highlight just so you see where things come from. This right here, I took the partial of that and got this, right? And here's my n, sorry, my m right here. That's what I'm putting right here. Partial with respect to x. Okay. Easy. Cancel, 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 cancel. H prime of x equals 1. Everybody see that?
Yes.
Which means that h of x is x. Just integrate. So, my solution, I'm going to jump straight to it, is x e to the x, or xy e to the x, that's the way we wrote it, plus 2y plus x equals c. Which you can actually solve for y easily now on that one. C minus x divided by x e to the x plus 2. All right, move this over here and factor out the left-hand side. You'll have y x e to the x plus 2 equals c minus x, which gives me a nice closed form solution. Questions about that? Yes, sir.
Last question we had, 4 steps. What did we miss?
Oh, 4, this is, 4 is writing it as there, right? So if you go back up to my list of steps, first thing I do is integrate then I take a partial and set it equal to, then I integrate again, and then I write the solution.
Okay.
Integrate, partial, integrate, solution. Actually, step B is you taking the partial and setting it equal to the other differential. Technically, there's 5 steps there, but that didn't include the 0 on my list of steps.
Episode 6, Return the Integrating Factor.
Nice. Question: what if the equation is not exact? Then the answer is make it. Use the force, Luke.
Make it exact.
Make it exact. Force it to be exact. Sometimes. Sometimes this will work. Actually, maybe not sometimes. I would say occasionally. Oh, actually, I would probably say, if we're lucky. The point here is that while in the technique for solving linear equations, we were always able to find the appropriate integrating factor to turn it into the product rule, we may, under the right circumstances, be able to find an integrating factor. It's almost more work than it's worth, but it's going to be one we can do, not too hard. Consider 2y minus 6x and 3x minus 4x squared over y, or y to the negative 1. It's not exact. You can convince yourself of that pretty quick. If I take the derivative of the first with respect to y, I get a 2. But when I take the derivative of this other one with respect to x, I get 2 terms. I get a 3 minus 8x, y to the minus 1. So it's not exact. So take mu and multiply through by it. I'm providing you with xy squared, the gift from on high. I've told you what an integrating factor would be. So if I multiply through by it, I get a 2xy cubed minus a 6x squared y squared. You see what I'm doing? I'm multiplying mu times both sides. Dx plus 3x squared y squared minus 4x cubed y dy equals everything. Mu times 0 is 0. Double check those powers that I got those right. Look good? Okay. So what's m sub y?
It's 6xy squared minus 12x squared.
Why?
Yeah.
And n sub x?
Exact same.
6x y squared minus 12x squared y. Okay? So there does exist some function out there that if I multiply through, turned it into an exact one. Okay? So the point here is that sometimes those things exist. I'm going to give you a circumstance where you can find it analytically. A lot of times, if you're reading somebody's paper that they are solving a differential equation model and they recognize that it's exact, they may have spent days or weeks or months playing with a differential equation that they couldn't solve analytically, and all of a sudden a bolt of lightning struck and there was an epiphany and they tried a certain integrating factor. They won't even tell you where it came from. They just discovered it or figured it out or played with it until they found one, multiplied it, and all of a sudden it's exact and they could solve the equation. You're like, where did that come from? It's like, I got lucky. I played the lottery. I tried everything I could think of and finally found one. So that happens in mathematics. There's a lot of those kinds of instances in the papers that you read in mathematics. Somebody just worked at it until they found something that would work, and we as students at an undergraduate level want to know, how did you come up with that? And the answer is they got lucky. They figured it out. They reverse engineered it until it worked. What I will show you now is a technique that will discover some of those for you through a process. But this is not the only process that might exist to do that. So this allows us to solve mu m dx plus mu n dy. And then we have to check whether or not our solution, that is, we're going to solve this differential equation right here, which is almost the same as this differential equation, except for the mu. And remember, you're only allowed to multiply through by mu as long as mu is non-zero. So you have to rule out those places where mu happens to be 0. I just wanted to make that point in there so that you know that even though you get a solution to the first differential equation, it's as long as mu of xy is not equal to 0. Okay, so how do we find the mu? I'm gonna adjust some of these. If you want to rewrite underneath here, you like the partial notation with subscripts better than my Leibniz. So I'm basically saying take m sub y minus n sub x and divide that by the original n and see what you get. Okay? So take the m, take its partial with respect to y. Notice that's the thing you're using to check if it's exact. So now that plays a role. And n sub x, you checked to see if it was exact. Subtract those and divide by the original function n. And if that depends only on x, no y's, then you can do e to the integral of m sub x minus, m sub y minus n sub x over n dx. I just rewrote the exact same formula, only now in subscript notation. And exp means e to the power. Then that will be an integrating factor that will turn it into an exact equation. I'll spare you the proof, but it works. Okay? Alternatively, if you have n sub x minus m sub y over m, depending only on y, then you can do e to the integral of n sub x minus m sub y over the m function dy. If we had more time, it would be a fun proof, but I'm not going to do it. All right, so let's do one. It's worth the effort of just going through and writing out what m sub y and n sub x are to see that they're not exact, because you're going to use those to try to find an integrating factor. So what is m sub y in this case? 1. And n sub x?
2xy minus 1.
So let's check.
2xy minus 1.
2xy again. Not exact, right? That's what that tells us. So my earlier technique will not work. There is no such f that when I take its partial with respect to x gives me m, and partial with respect to y gives me n. It doesn't exist. But I'm going to make it into one that's exact so that it will work. Let's do m sub y minus n sub x over n. What do I get? M sub y is 1 minus n sub x, which is 2xy minus 1 over n, which is x squared y minus x. Now that has x's and y's in it, but let's go through and simplify it if we can. Top is 2 minus 2xy. bottom I can pull an x out of and get xy minus 1. Top I can pull a 2 out. Agree so far? And what does that reduce to?
-2/x.
Alright, so just pull a minus sign out and turn this into xy minus 1, and you get -2/x. So you did the my minus nx over n, and you got a function that depends only on x. There are no y's. Okay? Alright, so if that's the case, since it only depends on x, then use mu is equal to e to the integral of -2/x dx. Which you'll see the log and it all,
Which is 1/squared.
that's derivative. Integral of -2/x. Oh, you jumped all the way ahead to, yes. what I was saying. Yeah, you're right. Sorry, I thought you were trying to do
No, I
the
was
derivative of this.
going to the end.
-2 natural log of x, which is e to the natural log of x raised to the -2, which is x to the -2, or 1/x squared. Thank you. Sorry. You with me?
Yes.
Now, what am I going to do with that mu? Yeah, so my new equation now becomes basically divide everything by x squared. Right? So 2 plus y x to the -2 times dx plus y minus x to the -1 dy equals 0. Took everything in there, multiplied it by 1/x squared. Or x to the -2. 2 plus y x to the -2 dx y minus x to the -1.
And then, but does that also mean that the solution will not exist at 0?
Yes. So if you were asked the question, what's the largest interval? What's the interval of definition, or the largest interval that the solution would be on? You could say, well, everywhere except anything that contained x equals 0 would not be a solution to this differential equation. Yes. Okay, let me clarify that, because that's a very good question. The solution we get from this technique will only be valid for x not equal to 0. But there is another solution to this differential equation that I just wrote down. And that's the solution mu of x, y, whatever that is, equals 0. 1/x squared equals 0. That will only ever be on x or y. Sorry, you got me overanalyzing this question. So this right here is actually just a point in this case. But you can imagine there might be circumstances like you get, let's just say we get like 3x. That's still just a point. It's still going to be, all right, never mind. This is a wasted effort. Not important enough to go down that road. What I said before is sufficient for now. It's not valid for anywhere where this is 0. Okay, so for x not equal to 0. We'll just put that off to the side there. Excellent. All right, is it exact? It should be now. Let's double check. Okay. The new m, sub y is x to the minus 2, correct?
Yes.
And n sub x is, should be,
Yeah.
x to the minus 2, right? So if you take negative x to the minus 1, you multiply that out front, you get a positive x. Subtracting 1, you get x to the minus 2, which is exactly what you need, okay? So yay, exact. Now, follow the steps. Dot, 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 dot. I'm going to write the answer and say that's 1/2 y squared minus y over x plus 2x equals c. When all is said and done, that's what you get. Okay? It's 10:38. You have your 2 minutes back that I took from you last time. We're even. I know the question asks on the evaluation, did he consistently let class out on time? So by not doing it this time and not doing it last time, the answer is no, but in the end, it all balances out. So please say yes.
I don't think I would ever answer the question.
That's the question I get the lowest ratings on every single semester. Everybody says no, he's always going overtime. So come on.
What? You can keep a student extra every day. It's like 10 minutes between classes. We're not at like an incredibly large university.